This is a video on how to calculate reaction forces on simply supported beams. So in my example, I'm considering a simply supported beam and there are two forces, 25 and 40 kilonewtons acting vertically down, and you'll see that I've got two supports on either end. And they're slightly different. One is a roller support and one is a simply supported pin joint. We need to look at these in a little bit more detail so that we can understand how to analyse them. Let's consider the one on the left first, the pin joint. So you can see in this diagram, you can imagine that this part of the beam is allowed to rotate. There's no resistance to rotation in this pin joint, but it does provide a resistance to forces in the vertical and the horizontal sense. In other words, it's not allowed to move up or down or across left and right. And to stop that from happening, we say that there are these reaction forces, and we put them on here: reaction in the Y direction, reaction in the X direction. Okay, so this is called a free body diagram because we remove the support, in this case the pin joint, and we replace it with the forces that particular joint produces. Let's look at the other one. So on the other side we had a roller support, similar in a sense that there are no moments at the joint, so it doesn't resist any sort of rotation, but it does prevent the beam from falling down, so there's no motion in the vertical sense allowed, so that is represented by this resisting force in the Y direction holding the structure up. But because it's on wheels, because it's on rollers, then it's considered to move in the horizontal sense. So therefore there is no resisting force in the horizontal sense. So there's only one force in the free body diagram. FBD is the free body diagram. Okay, so now let's go back to our problem where we have a pin joint and a roller support on either end. And then we can consider the free body diagram below here. So we've removed these two supports and we replaced them with the forces that they produce. This is our free body diagram, and this is the essence and how to solve problems in mechanics. Okay, so let's look at this free body diagram in a bit more detail then. We are considering an XY axis system here, and we've got the reaction here called RB, and the reaction on the other side called RA, and I've put in here a horizontal resisting reaction force, just labelled that as H. The other thing that we need to consider in how to analyse these free body diagrams is one of Newton's laws, where he said that if you consider the net, write this down here, let's get my pen, consider the net force in any particular direction, and he showed after a bit of manipulation that is equal to the mass times the acceleration in that particular direction. And you've probably seen this written down as more conventionally as F equals ma. We need to really put a bit more detail in here because forces, well, they're vectors, and we can usually represent that as a little arrow, so we can say the force in that particular direction in the horizontal sense is equal to the mass times the acceleration in that particular sense. And another way that we might represent that is maybe F subscript x equals mass times acceleration in the x direction. So the subscript shows the direction. Now the thing is that we don't have any acceleration in any direction here because this is a static problem. There's no motion, there's no acceleration. So this acceleration term is actually equal to 0, which means that the sum of the forces in any particular direction is equal to 0. And in fact, what we tend to say is we put in here a symbol to represent the sum, because when we sum them up, that gives us the net force, and you'll see in a moment how we do that with numbers. So we have the sum of the forces in the x direction equals 0. We've got an equivalent one in the y direction, because again there's no acceleration in the y direction, and there is also a moment version, so you can say that the moments at any particular point they add up to 0. And again, I'll show you what that means with this particular example. Okay, so let's just move along and do the analysis now. Well, we'll start with the easy one, which is in the horizontal direction. We've got here the sum of the forces in the x direction, we know, equals 0. What are the forces in the x direction? They're very simple. I'll just represent them with h here. And if you move across, there are no other forces in the horizontal direction. So let's write that down. Sum of the forces in the x direction, well, they're just h, and they equal 0. So don't get a simple equation than that. So now we go to the y direction. Let's do the same thing. I'll just write it over here. So the sum of the forces in the y direction has to equal 0. So now let's do that summing of forces in the y direction. What are they? Well, we've got a force here, RA. So let's write that one in. RA. Where's that pen gone? There it is. RA. And notice I've written that as positive because, according to my convention here, up is positive. And if I come across the beam, you'll see that the next vertical force is 25 kilonewtons. Work from the left and work your way across to the right. And the first one is 25. That's pointing down, so I'm going to make that negative 25. I know it's kilonewtons, I know it should be 25,000 newtons. But I'm going to keep the kilonewtons in the equation so that the answers come out in kilonewtons as well. That's okay as long as you're consistent. Moving along the beam, from left to right, the next force we come across is 40 kilonewtons. That is also pointing down, so we're going to make that negative 40. Move across the beam, don't forget there's also a force pointing up at the end that we have called RB to represent the reaction at point B. And they all add up to 0. Okay? So all of this stuff here on the left-hand side of the equation, that is me adding up the forces in the y direction and then setting them equal to 0. So we should just tidy this up and say, well, actually, we keep the unknowns on the left, RA plus RB, equals, well, we take the numbers to the other side, they become positive, so we have 40 plus 25, and that equals 65. Now, we can't solve that equation as it is because there are two unknowns, RA and RB. We've only got one equation. So we're going to need a second equation. I'll label that one equation 1. Now we've considered x and we've considered y directions, so the only thing that's left for us to do really now is to take moments. So the trick to taking moments is to take moments about a point about which there are unknown forces, because those unknown forces will be eliminated from your moment equation. Okay, so that's the key to doing that. In principle, you can take moments about any point. You really want to be smart about it and take the moments about the point about which there are or there are as many unknowns as possible. So let's do that. Let's choose a different colour. Okay, let's choose this one. So off we go. So we sum the forces now, the moment, about point A and set them equal to 0. So we'll take them about this point here, A on the left. So both the RA force and the H force, they are coincident at point A, so there's no perpendicular distance, to point A because they're actually at that point, so they're not going to produce any moments about that point. Great, that means they've disappeared out of the equations. So we move across to the next force, which is 25 kilonewtons. That is going to produce a moment because that 25 kilonewtons has to be multiplied by this perpendicular distance of 0.5 meters, and that will produce a moment which is clockwise. So let's define clockwise as being positive, so that we have 25 times 0.5, put that in a bracket and work it out in a minute, and that's positive. And then we're going to add in the next one. Let's open the bracket for the next one. So we move across the beam until we come across the next force, which is 40 kilonewtons, and that is going to be multiplied by the distance, or the distance now is going to be 0.5 plus 0.6, which is 1.1. That's the distance from the 40 kilonewtons, put it in here, from 40 kilonewtons force to the point A. Perpendicular distance is 1.1 meters. And again, it's going to produce a clockwise moment because that force is pointing down, so it will cause the whole beam to rotate clockwise about point A. So we'll make that positive. The next force we come across as we go towards the end of the beam is RB, and that's going to produce a negative moment because if you think about it, that's pushing the beam up, and therefore it will rotate the beam about point A in an anti-clockwise manner. So we'll make that a minus, and then the distance is actually the sum of 0.5 plus 0.6 plus 1.9, which is 3. So that's 3 times RB. And we have to set all of that equal to 0. Because all of this thing here is me summing up the moments about point A and then setting them equal to 0. Let's work it out. So first bracket, we've got 25 times a half, which is 12.5. Next bracket, we've got 40 times 1.1. Well, 40 times 1 is 40. 40 times 0.1 will be 0.4. So that, sorry, 4, sorry, so that would be 44. Yeah, that's right, yeah. And minus 3 RB will equal 0. Right, so what we're going to do, well, let's tidy it up. Let's take the 3RB to the other side to make it positive. And let's add up the numbers. 44 plus 12 is going to give us 56.5, isn't it? Yes. So finally, if we divide both sides by 3, like this, and that will tell us that RB is equal to whatever 56.5 divided by 3 is. So I'll get my little calculator here, and we'll do that now. So 56.5, divide that by 3, and it's about 18.83. Okay, so we'll have that. So 18.83, just 2 decimal places, and don't forget that was kilonewtons. Okay, so there's our answer for RB. Then it's a trivial exercise now to work out the other reaction force, RA, because we can use our first equation. So if we know, let's write it down here. RA plus RB equals 65. We can plug in the value of RB. We can say, well, RA plus 18.83 equals 65. To rearrange that, well, we want to get RA on its own. So we'll minus 18.83. And we'll get our calculator up again, and we'll do that. 65 minus 18.83 is 46.17. 46.17, and those are kilonewtons. So there you have it. There we have the two forces, reaction forces. The reaction force A on the left is 46 and a bit kilonewtons, and the reaction force on the right, RB, is 18.8 kilonewtons. This kind of makes sense if you think about it, because when you look at the beam, the forces are concentrated towards the left-hand side of the beam, so you'd expect this reaction force here on the left, RA, to take more of that load, and RB is not going to be carrying as much, so you'd expect that to be at a lower value, which it is from here. Okay, thank you.